Howdy guys, welcome back for part 2 of chapter 10 on gases. Some of this stuff will be, again, review from Chem 2 material, and then other stuff will be the new stuff. The good part is not too much of the new stuff actually winds up on the AP test. So there's going to be some stuff in here that doesn't really come up all that often, but we'll go over it just in case. All right, so starting off, Dalton's law of partial pressures. This is when you have a mixture of gases in the same container and they're not reacting, they're just all floating around in there. So, blow up a balloon, you've got some nitrogen in there, you got some oxygen, you got some carbon dioxide, they're just floating around, not reacting. What we say is the total pressure for that mixture is equal to the sum of the pressures that each gas would exert if they were by themselves. And that pressure of the individual gas is what we call a partial pressure. So in other words, the total pressure of that mixture is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3 and so on for however many gases are in there. So we like it when there's only 2, but real life there's often 3, 4, even more. All right. Well, from that we can talk about something called the mole fraction, and this is the more important part. And we did talk about this in Chem 2, but we phrased it a little bit differently. All right. So we say because each gas acts as if it's alone, we can relate that amount in a mixture to its partial pressure. So the pressure from gas 1 related to pressure of gas of the total pressure. So kind of this ratio. Well, we can use the ideal gas law and say, well, the moles of 1 times its constant times the temp divided by volume. Well, the total moles times that. Well, hey, wait a minute. R will cancel out. T will cancel out. V. Everything cancels out to say the pressure from gas 1 compared to the total pressure must be equal to the moles of gas 1 compared to the total moles. And that ratio of individual moles compared to total moles is what we call the mole fraction. It is usually written with the symbol chi, which is this fancy Greek X here. Sometimes you just get capital X because the fonts aren't there. But all it is how many moles for compound 1 divided by the total moles. You could also think of this kind of in terms of percentage, and that's what we did in Chem 2 more. If something is 75% of the mixture, 75% of the moles, well, that would be a mole fraction of 0.75. If something is 33% of the mixture, that's a mole fraction of 0.33. So these things are interchangeable. You just have to move the decimal to make it a percent. But that's the new thing, the mole fraction. All right. So this end result is saying, the pressure due to part 1 is, well, the mole of 1 divided by the total moles, which means it's the mole fraction of 1 times the pressure. So if the mole fraction is 0.75, well, then the pressure of 1 is 0.75 times the total pressure. Or again, 75% of the total pressure. And here's what I mean, where sometimes they don't use chi, they just use an X. You get used to it. All right. So that's Dalton's law and how we can apply it a lot of times. But mole fraction is the thing to remember there. Next up is, why does this happen? So these are our gas laws. We've always been talking about the gas laws. Boyle's law, Charles' law, combined law, ideal law. Laws tell us what happened. They do not tell us why. They just say this is what we observe under these conditions. Well, why? The explanation, or at least our prediction for the explanation, is a theory. And so what we come up with, and we often can't prove it right or wrong, or we say, well, this works for certain things. Remember, for certain things like VSEPR and hybrid orbital theory, they don't work for all conditions. We just say, well, they're useful here. So we're going to have a theory, the kinetic molecular theory, to say, why are these laws working under our normal conditions? All right. So here's the main tenets. We did do this in Chem 2. It's probably what we started with in the gas law section in Chem 2. We have the postulates, the statements that explain, that are the parts of kinetic molecular theory, often abbreviated KMT, that tell us why do gases behave the way they do. So we say gases are made up of particles, right? They're made of molecules or atoms that are in continuous random motion. They're always moving. They're flying in all 3 dimensions. They're going around. We say that the combined volume is negligible. It's really, really tiny compared to the total volume. I think in Chem 2 we normally say that the space between particles is incredibly large compared to the space the particles take up. That's the same thing, just kind of rephrased. We say that particles don't exert forces on each other. They don't attract each other. They don't repel each other. They're just flying in straight lines, whatever. Number 4, the energy can be transferred, but the average kinetic energy does not change. We said that the collisions are elastic, that the energy does not change when things collide with each other. And then going along with that, with number 5 here, the average kinetic energy is proportional only to the absolute temperature. Only to temperature matters. And so I have seen that on a practice test for AP, which was a former test, where they did all this stuff and said, we're changing pressure, we're changing volume, we're doing all this stuff. What happens to the average kinetic energy? And no matter all this stuff that they gave, the key thing was temperature is constant. And because temperature didn't change, the average kinetic energy did not change. And that was the answer they wanted on that multiple choice test. So knowing these postulates of the kinetic molecular theory can get you easy points on the test, because they're going to say, did you know kinetic energy only relies on temperature? Did you know that collisions don't change the energy? Did you know that gases are in constant motion? That's what they're looking for on some of the multiple choice questions. All right. Now this is the stuff that is not on the test, at least not that I've seen, but we're going to teach it just in case. We just said temperature is related to the average kinetic energy. Average kinetic energy. But that's the average. Individual particles can have different speeds, different amounts of energy. Some will have less energy. Some will have more energy. And if you have less energy, you'll be moving slower. If you have more energy, you'll be moving faster. So remember, temperature tells you the average. And this is the important part here. At the blue line is at 0 degrees Celsius, so the average energy is lower, and so we have more molecules that are moving slower. But then when we heat them up at 100, right, if we're just saying, where's 500 meters per second? At 100, it shifts. The whole graph moves to the right, and a larger proportion of molecules have that energy because the average energy has increased. Right? Now, for any temperature, or for any amount of, or any set of conditions, we have a graph that looks like this, and we have 3 key speeds. We have the UMP, which is the top of the curve. That is the most probable one, because if you see here on the y-axis, it's what fraction of molecules, what proportion, right? So if you're in stat class, this should look very familiar to you. So the top is the most probable. The U average is the average speed, and since we've got this longer tail, it pulls it up some. So it goes a little bit to the right. And then we have the root mean squared speed, which is the speed of a particle that has the average kinetic energy. And so that's even higher up. And this happens because we're squaring things and other stuff happens. But it gets pulled even further to the right. They're not all that different from each other. This is a little bit exaggerated for the scale. Not too exaggerated. But that root mean squared speed, that's the one we want to worry about, because that's where things go into our next gas law. So the key thing here with the root mean squared speed and molecular mass or molar mass, at any given temperature, the average kinetic energy is the same, which means this 1/2 mass times speed squared, right? That's kinetic energy, 1/2 mv squared. Well, the v is this URMS, the speed for the root mean squared. It's the same for 2 gases at the same temperature. The key is the masses are different. Well, that means the root mean squared speed will be equal to the square root, and this is coming from some derivation, don't worry about this, of 3RT divided by the molar mass. That capital M is molar mass. That means if you have a very large molar mass, this whole number becomes smaller, you'll have a slower speed. So here on this graph, oxygen is the heaviest graph. It has this lowest speed. Nitrogen's a little bit lighter, so it's a little bit faster. Water here is lighter. It's a little bit faster. When we get to lower and lower molar masses, well, then this number gets bigger and bigger, so the graph shifts to the right to higher speeds. So helium, molar mass of 4, it's shifted way off here to the right. Hydrogen, molar mass of 2, even further to the right. So that's just using these of where is the root mean squared speed. It all depends on the molar mass. And we can use that for another gas law that we did learn in Chem 2 about Graham's law of effusion. So we talk about effusion and diffusion. Effusion is when gases escape through a tiny hole in the container. So we've got some small hole there to scale and lots of gases up here, but over time gases might fly and happen to hit that hole perfectly, and now they can enter the other part. We see this most commonly with a balloon, right? A regular latex balloon has tiny holes in it, and over time the balloon gets smaller because over time gas molecules inside the balloon happen to find those tiny holes and they escape, and then there's less gas in the balloon and the balloon shrinks, right? Diffusion is when a gas spreads out, and diffusion also depends on molar mass. The lower the molar mass, it will go faster. The trick is, it isn't just a straight line. Gases bump into things. They bump into other gases. So this is, we're talking about, we have the net distance traveled, but the actual path that a gas travels is a lot longer. So you'll see on some of these graphs, it's saying, hey, these gases are traveling at 300 meters per second, 400 meters per second. These things are traveling very fast. Well, how come when someone opens up a container of perfume, it doesn't instantly travel 300 meters per second and get you, really quick, basically at the speed of sound? Why isn't it going at that fast? Because that gas molecule is taking a circuitous route. It is bouncing around and it takes time. It will still be the case that lighter molecules will spread out faster, but it takes extra time for diffusion. All right, so that's the two things there. So if we talk about Graham's law to describe these, the lighter gas will always travel at a faster rate of speed. So I always like to put the lighter gas on top here and say, what's my rate of the lighter one? And put the molar mass of the lighter gas on the bottom. That way I'll always get, for my answer, the lighter gas is X amount faster, or X times faster. So because if we go back here, the 3RT stays the same, only the molar mass will change for two different gases. That's why this simplifies to just, well, what's the square root of those two different molar masses? So we can see here, helium is a much lighter molar mass. It will be moving faster. It will be able to escape through the holes faster. That balloon deflates quickly, while the argon balloon with a higher molar mass hasn't changed much at all. All right. Last thing, and this is another new thing that we didn't talk about Chem 2, and this does get mentioned on the AP test. In real-world gases, the equations, especially the ideal gas law, doesn't really work that great. It works well at relatively high temperatures and relatively low pressures. Well, what does that mean? High temperature, it could be room temperature for some things like oxygen and nitrogen. Yeah, room temperature is a high temperature, great. But for things like water, well, water should be a liquid at room temperature. There is some humidity in the air, there is some water vapor, but things are happening because they might stick to each other when they bump into each other because they don't have enough energy. So for other gases, we need to go even higher and higher, 400 degrees, 500 degrees, 600 degrees. We have to go high temp. So it depends on the gas. For low pressure, that also depends on the gas. But if you see here this little insert, this is graphing PV over RT, which should be equal to 1 for 1 mole of gas. And they're saying, well, what happens as we compare that to raising the pressure? Well, as you can see, at very low pressures, between 0 and 1, it's pretty good. It's right there equal to 1. But there's even some gases where right around 1 atm, they're starting to deviate from ideal behavior. The graphs are veering off. And you can see here when we scale out to going very high pressures, 1,000 atm, some do this weird thing where they drop down and then go back up and all that. Others, like hydrogen, they just start going up. And they veer off of what an ideal gas should be on this dotted line. So we say, okay, real gases at higher pressures or lower temperatures, they don't behave like an ideal gas. Why not, and how can we work with that? The reason they deviate is we say, okay, one of our postulates, the gases take up pretty much no space at all in a container. Well, if you got high pressure, those gases are forced to be closer and closer to each other. Now they do start taking up a decent amount of space in that container. So that's going to lead to some deviations. The other one is we said that for ideal gases in the kinetic molecular theory, that they do not exert forces on one another. Well, in a real gas, yes, they do. They maybe stick together some, or maybe in a mixture, they repel each other. These things are going to cause differences in how much pressure they get exerted on, or how much they're going to move, or how they're going to snap together, and do they bounce right off? Does energy keep going into kinetic energy, or does it go into a bond being formed? These things, cause deviations. So at low pressure, we're pretty good. At high temperature, where you have lots of energy to overcome any forces, we're pretty good. But at higher pressures and low temperatures, they're going to stick to each other. They're going to take up too much space, and the ideal gas law just won't work well. So we have to have a different one. So we can correct for it. We call it the van der Waals equation, where we adjust the pressure because molecules do attract and repel each other. We're going to adjust for volume because molecules take up space on their own. So it's still going to sort of look like the ideal gas law. We're going to make some corrections to it, and it's this one. The good news is you don't have to memorize this one. If they put it on the test, they will give you this equation. But notice here, this is the pressure term, but there's a volume in there. There's a number of moles in there. This is for the attraction of other gases, and there's this A term. And you see here there's a table that gives you the A terms. And then for volume, it's not just volume, it's also, well, how much space is being taken up. So they're subtracting off the space of the different molecules. So again, depends on the number of moles, depends on constant B, which is over here. And you can see the very small atoms have smaller numbers. The larger molecules have larger numbers because they take up more space. But that's how you correct for that. And then that equals nRT still. So that half of the ideal gas law didn't change. The key thing is you're never going to be asked to you might be asked to memorize this, but you're going to be given these numbers if it ever comes up. And so it's more of, can you plug the numbers in? Can you understand the rationalization that we have to adjust, and this is the important part, do we have to adjust that molecules and particles and gases, they do attract and repel each other. They really do. That they do take up some space. And so if it doesn't follow the ideal gas law, it's one of these things or both that we have to account for. That brings us to the end of the chapter. So don't worry about this stuff too much. Like I said, it's more of given information that you just have to apply better. But that finishes off chapter 10 for us, and I'll see you guys in class soon.